Okay. For those of you who may not remember, but 40 years ago, we had sample return missions, autonomous sample return missions, that were highly successful. And in 1976, the automated Lunar 24 spacecraft landed in Mare Crisium. It had this drill, which is now actually shown depositing the sample into the spacecraft, that drilled into the surface, extracted a drill core sample, and the samples were sent back to the Earth and safely recovered. Very lovely success story. Note the size of the landing spacecraft, 4.5 meters high. I'm going to give a little history here and a little bit of apology, but it's important for those young scientists in the audience to recognize that sometimes people do make mistakes, but the way science evolves is they're recoverable. One of the first papers I presented was at AGU and then later published in JGR, discussed the Apollo 17 site and dark mantling material. And in that paper, this was just before Apollo 17 landed, we predicted that the Apollo 17 soils would be very titanium rich. And lo and behold, we were correct. But we were correct for the wrong reason, we now know. That's a whole nother story. But that gave us confidence that when the Russians sent their spacecraft to Mare Crisium and landed, we looked at our data and found, oh yes, we have data for Mare Crisium. Now these are 40-year-old data. They were Vidicons at the time and filter photometer measurements, but we were quite confident. So we made a prediction of what we expected the Lunar 24 samples to be, and in particular compared them to Apollo 12 and Luna 16, which were low titanium basalts, and we thought that was quite safe. Well, of course, when the samples returned and were reported what the composition was, the Luna 24 samples were completely new. They were very low titanium basalts, on the order of 1% or less. They were very immature. Fragments of these kinds of basalt had been found in some of the Apollo samples, but this was an entirely new basalt type and clearly well identified by these return samples. And that was reported, of course, in 1977, and we had a little bit of mud on our face because we never predicted that such samples existed in extensive manner. So the next set of papers sort of were backpedaling. Well, it's a very complex area. Here's one of the early maps that shows, yes, we had spectra, but we didn't really have spectra of the place they sampled. And it's a very complex environment. And two more papers basically said the same thing. We looked at the samples more and showed that, yes, in fact, where they sampled has really a complex, unusual kind of both spectral character with the data we had at the time, as well as unusual geomorphology properties. So that's sort of how it got left. In addition to the basic immature character and very low titanium, it raised a whole nother questions about the whole calibration of how you make predictions on titanium content, and that has gone on for decades. I'm not going to go into that because really I'm going to report on a happier, successful story. Again, in summary, the Luna 24 basalts that were returned, these were the last samples to be returned from the moon, by the way. They identified a new and very major class of basalt type, except for these few fragments that had been found in Apollo samples. And they were very low titanium, on the order of 1% or less, and showed very low to very low maturity. No well-developed soils, very little space weathering activities. Okay, jump forward 40 years. Here we are with this wonderful array of new data. And Mark Robinson has a lovely paper that's just come out that discusses not only Apollo landing sites, but the Luna landing sites. And here's the Luna 24 lander right next to a fresh crater in Mare Crisium. There it is a little closer in detail. The NAC data have been really remarkable because, of course, they give us a really good close-up view of the surface. And what's been noticed by several investigators is that the area in Mare Crisium is strewn by a large group of secondary craters. It's clear they're secondary craters. And several researchers have pointed out that these are likely to be due to be secondaries from Giordano Bruno. And my co-author, Sasha Basilevsky, is one such person who's done very detailed analysis of this and has done some recent crater counting and finds that his results are very comparable to some of those, a couple of years ago, namely that these secondaries in Giordano Bruno are on the order of less than 10 million years. Sasha believes it's between 5 and 10 million years. Other people push it up to closer to 1 million years as well. But there's no doubt, or at least there's a consensus, I should say, that these secondaries, that this group of craters are secondaries, and they're most likely linked to Giordano Bruno. That's really exciting, I think. Here's the context. There's Luna 24 there. Here's Giordano Bruno. Look at these. I'm going to show you some M-cube data soon. So here's the two large craters, Fahrenheit, and I don't know what the name of that one is, but here's Luna 24. So look at this spatial relationship, because I'll show you some M-cube data that has those features in it as well. Okay, here's some M-cube data of that, and I'm very pleased to say that what I'm going to be showing you is what we call targeted M-cube data. This is our high resolution, our full resolution of the instrument. We only have a handful of images from this, and we were thrilled to see that one of our full resolution data occurred with the Luna 24 site. And that's what I'm showing you today is our best data, and it's really nice. I wish we had the whole moon with this. Here's these two craters I was pointing out, and here's the landing site, which you can't really see. Here it is in basically albedo in the middle of the near-infrared where there's no dramatic absorption bands. Here's the long wavelengths, which has a little bit of thermal component. And here's our two integrated band strengths across the 1 micron band and the 2 micron band. And these data in this form really show you where fresh material is excavated. And it's peppered by these group of secondaries. You know, the bright in both of these is concentrations of these secondary craters. Again, these two large craters, but you can see a lot of this region is some of these features that I was just showing. And in fact, for those of you who have really good, this is that little group of craters that I was showing you before here. I'm going to concentrate on this crater right here because it's large enough to get some really good M-cube spectra. First of all, overall region, this top spectrum is not from this region. It's from the strip included some of the highland areas to the south in Mare Crisium, and it just shows you that in the highlands there's nothing there. It's nice, very feldspathic, very low mafic rich. So that gives you a sense of the character of the data. All these are from various areas around this region, some with very strong absorptions, some with weaker but still prominent absorptions, which are the character of the soils in the area. If we take this and do a continuum removal to evaluate the character of the spectra, here's again that featureless spectrum, nothing there, okay. A group of soils which actually have a 10% band, so they're still prominent bands, but these fresh craters have a very strong band. But if you look at the character of these, and for those of you who are spectroscopists, they have relatively long wavelengths. This is due to the high calcium pyroxenes that occur in the basalts. And the second thing you can see is that really the character of these bands throughout all these spectra, whether the soils or the various craters, are pretty comparable. It shows that it's a relatively homogeneous group of basalts, regardless of which crater you're examining. Here's that little crater that I was showing you down here. Here's Luna 24. Nice. M-cube data compared to NAC data looks sort of fuzzy, but this is the best we can do. But it's good enough so that we can do a traverse across this, and you can see how the spectra evolve or demonstrate from the very fresh crater or fresh material excavated by these secondaries into the surrounding soils. And again, this is our nice full resolution targeted data, and they're beautiful. I just love these. Going from a really lovely basaltic exposure in the center of these secondaries down to surrounding soils. And this essentially is a good example of the kind of data in the Luna 24 region in terms of this mixing between soils that have some maturity associated with it and very freshly exposed material, very beautiful basalts. For comparison, here are some of the Luna samples that we have in the Relab collection, and of course they sort of look now like what we see in the remote measurements. This is very reassuring. Wish we had these data 40 years ago, but at least we have them now today. And now, here's my summary slide. The summary, it all makes sense now. It's taken me 40 years, but this is a really happy story. The enigma we've had for the last 40 years of these high iron basalts, very low titanium and immature, but now with the NAC data that really has helped us understand the geology of the site, and with the spectral data, it now gives us a much more complete understanding of the character of the Luna 24 samples. Thank you.
Tim Swindle had a paper out trying to use the Luna 24 data to say something about the age of Chrysium Basin itself. Now, most of the material we're getting is not from Chrysium. That's more Mari and the rest. But can we say anything now that we have a better feeling for the spectra and the geologic context and everything else as to whether we actually do have a good age for Chrysium, or whether we sampled it in this in a secondary crater ejector?
I don't think I can answer that. Maybe Sasha has a thought. But what Sasha, based on this study, is going to be doing with the sample people there in Russia is going back and looking at the samples to see if there's any fragments of the secondary source. And that's certainly an area that they're really interested in pursuing now that they know the geologic context. For age, I don't know how any of the spectra are going to be able to address that any further.
Okay. Yeah, this is more just a matter of getting, now we have the context, so now maybe we can say more profound things. So,
yeah.
Anyway.
Yeah. Okay, thank you.
All that work was really good, and it was low resolution, crappy data by today's standards. It was wonderful by then, right? Yeah. But it was good work, except they had it all 78 paper, but all the other ones were good. Yeah. But what on that bottom bullet right there? What is different about the Spectra relative to the old Spectra? Is it because we pulled up subsurface material that's different than the big broad pixels that you were looking at in 1972?
Well, it's mostly that we have full spectral resolution spectra that have sufficiently high spatial resolution that we can see this kind of sequence. Before, we just had mostly 25 filters in the extended visible, and we were trying to understand the character of the basin from that. We did our best, but you're not always right. Yeah. But you did our best.
Just one comment for the young people in the audience, that the idea that those are secondaries from Giordano Bruno goes back to proceedings of the 8th with Butler and Morrison.
Yeah.
I think it's 77 or 78, something like that. Yeah. So that is not a new idea.
Yeah.
Right?
Yeah.
I know you knew that. Right? Okay.
But you do have to admit, Mark, that the NAC data help really confirm that and help do the age dating that people are doing now. Yeah.
But it's not a new idea.
Yeah, you're right. You're absolutely